Sai Ram and welcome to the next session in computational linear algebra. In this session, let us try and solve a few problems using the elimination method which we have recently learnt. Let's begin this session with a prayer. Om Sai Ishwaraya Vidmahe Satya Devaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. Okay, we begin with a very simple problem. We have three equations in three variables, and let's try and solve this. Okay, here it is. I picked up the coefficient matrix here. Okay, let's keep the B separately, and we will operate on B as we finish our row operations on A. Okay, so the first pivot is quite clear. The first pivot is 1. So let's try and find what's the multiplier for the second row so that we can eliminate this element. A21 element, we'll have to remove that, and therefore the multiplier is denoted by L21, right? So this is a notation that's being used. So we can so let's find this multiplier. The multiplier is going to be this coefficient A21 divided by the pivot, so 1 by 1, that is 1, and the row operation is going to be R2 minus the multiplier times R1. Okay, so let's do that. So when we perform this, we get 0 0 minus 2, and something interesting that's happening here is that we attempted to remove this, but the third one has disappeared. I mean the second element also has disappeared. Okay, fine, but let's just proceed with elimination. Let's not do any action at this point. The next step supposedly in elimination is to eliminate A31 element. So let's find the multiplier for it. This is this coefficient divided by this pivot, therefore that's 1, and the operation is going to be R3 minus 1, L31 times R1, which is the L31 is just 1. Okay, when we perform this, we find that we get 0 minus 2 and 0. Okay, now we have to look at eliminating minus 2, right? But if we try to eliminate minus 2, of course, the elimination method says look at this recursively and we'll have to eliminate this. But when we look at this whole picture, there's one more way to eliminate minus 2. We can even look at the first row and try to eliminate the minus 2 in the third row. But remember, when you do that, when we try to eliminate minus 2, we may land up introducing something in the other elements which have already gone to 0, right? So therefore, trying this idea with R1 may not be a good idea. So we'll have to look at eliminating it only with row 2. But the problem with row 2 is that the pivot in the pivot position here, this is gone, right? The second pivot at this position is 0. So we don't call it a pivot anymore. We just say that there is no second pivot. That's how we are going to say. And the solution now comes by trying to exchange rows 2 and 3, because we see that there is something non-zero here, right? So let's exchange row 2 and row 3. And now, something interesting, when we exchange rows 2 and rows 3, we find that we are getting an upper triangular matrix, and the interesting thing is there are 3 pivots, which means that there is only one solution, right? So immediate scenario change. We felt as if the number of pivots are lesser here because 1 is seemingly 0, but the moment we exchange the rows, we are able to figure out that it is not a elimination failure, but it's not, the number of pivots are still 3, and we are going to find the solution. Okay, so let's apply this same operations on the B vector. So after applying all those operations, you can please check this. I'm getting this value 7 minus 4 and minus 2, and let's put these equations down here and use back substitution, and we get this answer. So the answer is 4, 2 and 1. Okay. So that should be a pretty simple example just to review elimination. Let's move to the next problem. Again, we are having 3 variables and 3 equations. Okay, and we have got the coefficient matrix. B I have written separately as a vector 7 5 3. Calculate the first pivot. Okay, the first pivot is clear here. First multiplier is going to be this coefficient divided by 1, so that's 1. So let's do the subtraction. Again, we find that though we attempted to make this 0, here also we find a 0, doesn't matter. Let's just proceed with elimination again. So this time we have -1 here, we'll have to eliminate this. So the coefficient divided by the pivot, so -1 divided by 1, that's -1. So our multiplier for L31 is -1. So let's do this operation. And when we do this operation, we find here that we are landing up with 0, 0, -2, 0, 0, 2 here, right? So the third row basically is becoming 0, 0, 2, right? Now, do we have an opportunity for row exchange, right? Do we have an opportunity for row exchange? In case there was something non-zero here, yes, there was. But now, I doubt even changing them is not going to help us, right? This means that the elimination, or we are clear that the number of pivots is definitely not 3, right? There is a number of pivots is going to be less than 3, right? Okay, so that's what the statements say. Therefore, we'll have to stop the procedure. We have found its upper triangular and we are stopping it, right? Okay, but let's see in the case when we know that this is a singular case, because the number of pivots are less than 3. Which is a subcase, is it going to talk about infinite solutions, or is it going to talk about no solution, right? So let's decide that. We can decide that only by performing the same operations on B. So when I perform these operations, I get a value 7, -2 and 10. So let's substitute this here and we find the values are here. We get 2z equal to 10 from the third equation, so I get z equal to 5. And -2, right, we may tend to make this mistake of saying -2y, but remember the second row into this vector, so it's a -2z equal to -2, and that value is z equal to 1, which means that there is an inconsistency, right? The third equation gives us 5, but the second equation gives us 1, and therefore we have to say that there is no solution to this linear system of equations. But the interesting part is, what if we change the original B vector is 7, 5 and 3. Suppose we change it to 7, 5 and -5, right? And perform the same operations, I get this answer. And if I try to look at this, if we see the third equations, 2z equal to 2 gives us z equal to 1, and -2z equal to -2 also gives us z equal to 1, which is consistent, right? Which means that if I fix my z, the remaining things must come from a first equation, right? And that's what we are writing here. So the first equation is x plus y plus z is equal to 7. Since z is given to be 1, we are calculating that x plus y should become 6, right? That means that this is becoming infinite solutions. How infinite? Z is fixed to be 1 and the remaining is to be put in these two, right? So I can pick up 1 5 or say 5 1. There are millions of such numbers, and that's why this is infinite solutions, right? So how do you understand this diagram? This is like z equal to 1 is the plane that's passing parallel to the xy plane at the value 1 on the z axis, right? So, and then you imagine a line there on that plane having x plus y equal to 6, right? So maybe this is a negative slope line. So if we try and draw this, you will be able to figure out that so the linear system is coming down to a line, right? Which means that it is it has got infinite solutions. Okay, let me move to the next problem. So this problem, the questions are going to be part by part. Okay, here we are not given linear system, we are just given the coefficient matrix. First question is, what's the first pivot? That's pretty simple, so we are able to figure out the first pivot is here, so that is going to be 1. Okay, so next question is, what's the second pivot? Right, so when we are asked for the second pivot, remember that we shouldn't directly go to A22 and say that that's my second pivot. Remember, pivots come out in the process of elimination. So let's try and do the elimination and then talk about the second pivot, right? So let's move, try and operate, make a row operation there. So we get the multiplier is this coefficient divided by the pivot, that's 1. So R2 minus 1 times R1. So let's do this row operation and we get 0, 1 and 1. So we need not worry about the third row, we just are bothered about the second row. And before we can proceed, I think we have got this pivot and therefore the second pivot can be understood as 1. Okay, let's move to the third part. So this part says what entry at 2 2, right? So here is the entry, right? This is the entry 2 2. Would force an exchange of R2 and R3, right? So interesting question. Now, when would we exchange these two rows? We would exchange these two rows only if there is a 0 that comes in this position after doing my row operation, right? And when we had a 2 here, we got the answer to be 1, which is non-zero, so there is no problem. But what if there was a 1 here and we perform the same operation? I think this element is going to go to 0, so that must be the answer. So that's it, right? So if we in the original coefficient, if we had a2 to be 1, then this would force an exchange for us of the rows, row 2 and row 3, right? Okay, so let's move to the next part. Okay, interesting. What happens when a33 equal to 1? Okay, now why is that question asked? So what we'll do is we'll try and figure out what's the third pivot, and that might help us understand what they're asking. So assume that this is the same, and we have got a 1 here, right? Instead of 2, we have got a 1 here. Now we will have to remember, we have to eliminate this element, right? Next one to go is going to be the a32, and we are able to get the multiplier. Here is the second pivot, so 1 by 1. That's so. Let's do r3 minus r2, and when we do this, yes, this is gone. But unfortunately, this also goes, which means that the third pivot disappears, right? And what does that convey to us? That elimination fails and the third pivot goes to 0, right? So let's check what's the answer, right? So that's what we get. The third pivot has gone to 0. But more important than understanding this is to talk about what will happen to the right hand side if it is given, right? So here is the answer for that. If the same row operations on B lead to the third element going to 0, right? So here is the important point. So we find that the third pivot has gone to 0, and we find if the third element goes to 0 on the same row operations on B, then we are going to have infinite solutions, right? If not, if it is a non-zero element there, then we are not going to have any solution, right? So do think about this part. Let's move to the next problem. For each of these problems, I would request that maybe it is better if you could pause the video at that point and think about the solution. It won't help you actually if we just state the problem and the solution. It's good to think about it. Anyway, okay, so here is an interesting problem. They have not given us the coefficients, it's just given us variables here. So anyway, ax plus by is 2 and cx plus dy is given to be 9. So right hand side is given. If x equal to p and y equal to q solves this linear system, so that's a solution, right? That's what they're saying, that this is a solution. Now we don't know if it is part of the infinite solutions or a single solution. Okay, we don't know that, but that doesn't matter, right? We know that it solves the linear system. Then find the solution if the right hand side changes to 8 and 36, right? How do you think about this? So this part is given. Obviously we can't go about doing elimination in order to solve this because it's not in the numbers are not given to us. So we need to look at the pictures that we have studied, right? You should talk about the row picture, or we should talk about the column picture. So which is going to help us here, right? So that is the important crux. So think about it and let's move forward to the solution. Okay. Now the easier way is to look at the column picture, and if we write it in the columns, there is a very easy way that we can understand the solution. Okay, so this can be written as AC is one column, BD is other column, and we can put as AC times x plus BD times y equal to 2, 9. Okay, now we know that P, Q solves this equation. Therefore, this equation holds when I substitute for x P and when I substitute for y as Q. Okay, now look at the right hand side 2, 9, and look at the new right hand side, which is 8 and 36. So I can get to the new right hand side if I am able to multiply the right hand side by 4, right? And therefore we get 4 and 36. Sorry, this must be an 8 here. This must be an 8 here. Sorry for the mistake. Okay, so this will lead us to understand what's going to happen on the left hand side, right? So since we multiplied the right hand side by 4, let's multiply the entire left hand side by 4. Then the equation holds. Okay, so now we have something interesting. We have this entire linear combination of these two columns times 4 is equal to 8, 36, right? So all that we need is simple. Just take the 4 inside, and if we pick up the 4, move it inside. We know that remember that the equations as such is not changing, but if we are able to, let's just take the 4 inside now. Let's say this will become 4p and 4q. We are just distributing distributive law we are applying here and then making this. So this equation must be correct. Now the interesting part is, when you write this down as a linear system of equations, remember that the coefficients don't change, right? The coefficients doesn't change. And we have got the right hand side to be, again there's a typo here, this must be an 8, 36, right? We have got the right hand side to be 8 and 36, and we know that it's given by the linear combination of the same columns, but this time using the scalars 4p and 4q, and therefore what's the solution to the new equation? The solution is 4p and 4q, right? Okay, let's move to the next problem. Okay, here is another quite similar like the previous one, because I see that they are not given us one coefficient here, and we can see there is one more coefficient. I mean, sorry, there is something that's missing on the right hand side. Okay, so here's the first part. In this linear system, it says choose a b to make this linear system singular, right? So what do we mean by singular? We will have to choose this b so that the number of pivots does not become 2, as simple as that, right? Let's not worry about the solution. We should talk about making this system singular, and that can happen only if we make the number of pivots to be less than 2. If the number of pivots come out to be 2, then we have got a single solution, which is a non-singular case, right? Therefore, let's go ahead with this. So we have here 2 and 4, that's the first pivot, that's 2, and we want to eliminate 4. So if we have to eliminate this, my multiplier is going to be 4 divided by 2, that is going to be 2. So if I want, so ultimately I am going to subtract from 8, I am going to subtract 2b, and therefore what should be my b so that this disappears? I think it's going to be 8 by 2, which is 4, right? So let's check this. That's it, as simple as that. Okay, now the next part says, can you choose this g to make this solvable, right? So question to be clear, it says you will have to choose the g after choosing this b. So which means that we have assumed that we have taken b to be 4. Okay, still can we choose this so that we can make this solvable, which means we will have to subtract this goes to 0, obviously this goes to 0, twice this equation, this element also goes to 0. So that is why we chose b to be 4. Okay, now question is, when we are looking at the second equation and both the coefficients are going to go to 0, this becomes solvable. Remember that the second pivot is gone now, right? There is no second pivot. The only way to get a solution is by moving to what is called as the infinite solution case. That can happen if the right hand side also goes to 0, and therefore we see that there is just one equation in 2 variables, and therefore it becomes infinite solutions. Okay, so which means essentially you are saying, when we do this row operation, yes, this goes to 0. After the row operation, we want g to go to 0, which means g minus twice 16 must be 0, which means that g must be 32, right? And that's the solution that we are seeing here. Okay, so let's move to the next problem. Okay, so we have here another set of equations, but interesting part is the same k is being used across in both the equations. Okay, for which values of k does elimination break down, right? When you say when does elimination break down, elimination breaking down is nothing but number of pivots becoming less than 2 in the 2 by 2 case, or talking about a singular case, whichever way we put it. There could be questions on saying when does elimination break down. Idea is simple. When do we land up in a singular case, or when do we land up in a number of pivots less than what's required for a single solution case. Okay, so looking at this, right, there is one thing that often strikes me. So I would like to actually substitute 0 for k and then try and see if it becomes singular. So try and do this. You will find that here y will become 2 and x will become minus 2, which is a clean solution. I mean, it doesn't break down at all. So that's the first argument to remember, right? If you try to put k equal to 0, we are able to solve this equation. And if you use elimination, what this answer says is that you can actually do a row exchange here, right? Because this becomes 0, so you can push this equation top, get this down, and we have both the pivots now. You will have 3x equal to 6 here, and 3x will become minus 6, and then 3y comes down saying 3y equal to 6, and we can get a single solution. Even by elimination we are able to get the same approach. So we need to think carefully and find out the k, and here it is. So if we try to make k as 3, right, then what would happen? We get 3x plus 3y is 6, and 3x plus 3y equal to minus 6, and it's clear that there is no solution just by looking at equations here. But if you attempt and do an elimination, we will find that the second equation here you will get a 0 and 0, but this one will become minus 6, which will become minus 12, and therefore there is no solution. Okay, so that's one case for which elimination is breaking down. Okay, not bad. Now what if this gives us a clue, right? Yes, we put k equal to 3 and we subtract this r2 minus r1, both these go to 0, but this one gives us an idea. Minus 6 is becoming minus 12, and therefore we are saying there is no solution. So can we think of the infinite solution case, right? So this must give us the hint to talk about the infinite solution case. If we substitute k equal to minus 3, we are going to get infinite solutions. How did that happen? Because if this is a minus 3, and you can think of it and see, this time the multiplier is going to become a minus 1, not a 1, and effectively you will when you add up, right, you will find that this goes to 0, and which means that the second equation becomes consistent, which is 0 0, and the right hand side also being 0. Ultimately we are left with one equation in two variables, which means that it is infinite solutions, right? So these are the two most important parts where we are able to say that we have no solution and infinite solutions. Now we can also give k equal to 0 as the answer, because though we know that that's a single solution, initially there was a pivot disappearing, right? When we put k equal to 0, the pivot was disappearing. So this can be mentioned, saying that for k equal to 0, we find that the first pivot disappears, but we can get the solution by a row exchange, right? So that can be mentioned. Okay, so let's move ahead to another interesting question. So this is it is not even giving us the coefficient matrix. It's only asking this question saying, I have A, seemingly the corner entry, right? So I can figure out something here. The corner entry A 5 5, so it must be a 5 by 5 coefficient matrix. That one is said to be 11. Okay, and the last pivot of A is U, right? So U stands for the upper triangular matrix, is going to be 4. So remember that we had the last element in the diagonal being 11, and it gets changed. The last pivot is 4. Okay, so the original value is 11 and it has got changed to 4. Okay. Okay, and the question says, what is the different entry in A, original, that can make A singular? What is the point then? We want to make the last pivot, should I say, there should not be the last pivot, right? Which means that this entry in the upper triangular matrix at 5 5 must go to 0. So that must be our idea. Now one common mistake that we could do is we may assume that we have got this upper triangular matrix, this element, by one row operation with the previous row, maybe with the fourth row. Now remember, that's not the case. If you're looking at the fifth row, then at least there have been 4 different row operations that have happened, right? So let's see what are the row operations that should have happened. So here is the idea. If we are saying it has changed to A55 to U55, how many different row operations, right? So using row operation, how many, right? How many row operations have we done? We have actually done 4 row operations. And reason why I'm saying 4 row operations is that no other pivot has disappeared before. The question clearly says that this is the last pivot. The last pivot is appearing at 5 5 means that the previous pivots are all available. Okay. And this is the important equation that we must remember and try to derive, right? So A55 original has got a subtraction by the L51 multiplier. Remember what is L51? L51 is coefficient A51 divided by the first pivot A11 times that element which was present. Sorry, this is slightly wrong. Actually, it's fine, because I was thinking that I should have mentioned the pivots here, but it doesn't matter. So we look at L51. L51 is the first multiplier. The first multiplier is got by the A51 divided by the first pivot, which is probably in A11. So we took the first multiplier and the last element or the fifth element of the first row, we have subtracted them, right? Now this is the new A55, or should I say A55 dash, right? So from this we are going to subtract L52, the second multiplier, times now A25, second row, fifth column. Similarly, you can understand the remaining, and we are actually doing 4 different row operations. And therefore, question is, what should we change this to so that we lose the last pivot, right? So let's say A55, what's the value? So that's 11, right? So 11 minus all these row operations are making it 4, right? So 11 minus all these row operations are making it 4. So what does this mean? That means that this difference is 7. That only can make this 4. Effectively, all row operations are reducing it by 7. Okay, and therefore the answer is simple. In order to make this pivot disappear, all that we need is we have to set the original A55 should become 7. That's it, right? So that must be the answer. Right, I hope this session was useful and we get an idea of what kind of problems we have and how to go about solving them. Okay, let's end this session with a prayer. Om Shanti Shanti Shanti.